All right, in this problem says the accompanying figure shows a cross section of a long hollow cylindrical conductor of inner radius 3 centimeters and outer radius 5 centimeters. A 50 amp current distributed uniformly across the cross section flows into the page. Calculate the magnetic field at R equal to 2 centimeters, 4 centimeters, and 6 centimeters. Okay, so the current is flowing into the page. Okay, the current is 50 amps. Okay, what we'll need is the current density. The current density is the current divided by the area through which it's flowing, and it'll be the current density is also constant because the current is flowing uniformly throughout the area, and the area is just pi r outer radius square minus r inner radius square. So that's the current density. Now, what Ampere's law says is a line integral of the magnetic field around a closed loop is equal to mu naught times the current, the surface integral of the current density. Okay, so now what we're going to do is we are going to, for the three regions, we're going to draw a loop like that. That's for the first one, second one, and the third loop. I'll number them 1, 2, 3. Okay, so what we're going to do is take this line integral. What we're going to do is take this line integral around these three loops, 1, 2, 3, for those three regions. Okay. And so let's do that. So for loop 1, the field has to be 0 because from the symmetry of the problem, well, there's no current density, so this integral is 0. In the hollow, there's no current flowing, so this current is 0. This is 0, implying the field inside is 0. The field inside the hollow region is 0. All right, we'll have to add paper since all right, so now to region 2. In this region, so here is the loop, okay, and now we're doing an integral along this loop. The current is flowing in, so the magnetic field is pointing like that. If you, oh, no, the magnetic field will be pointing like this. So let me erase that. Okay. And the line integral, so we'll be taking the line integral in this sense. So the line integral, so oops, there is R is, and the current through that is through this region. Okay, and that this area is pi r square minus pi, we'll call this r in. All right, so this is equal to b times 2 pi r, and that's equal to mu naught times j dot dA. So b times 2 pi r equal to mu naught times j is I over pi r naught square minus r in square, and that's constant, and it's just this area, which is pi r square minus r in square. All right, so even though this expression looks ugly, well, it does look ugly, we'll clean it up. Also, so what we are saying is the magnetic field in this region, okay, again, the magnetic field is in that sense, and at a distance r from the center, the magnetic field is given by, okay, so let's clean this expression up. The pi cancels, and we'll get a 2 pi from here. It's the magnetic field is given by mu naught I by 2 pi, and r square minus r in square divided by r o square minus r in square times 1 over r. So that's the magnetic field inside. All right, now let's do the last part. So let's add another sheet. Okay, so for curve 3, okay, so there's where the current is flowing, and we are finding the magnetic field at a distance r, and again the magnetic field is like that, and so now since we are out here, the entire current comes into play. Okay, so this is equal to B times 2 pi r. It's equal to mu naught times I, the entire current. Okay, the current density integrated over the whole region is I. Okay, so B is just mu naught I over 2 pi r, which is the expression for a current if which would be the same. So the magnetic field at this point would be the same. It's the same as if this were a thin wire at the center. Okay? So once you're outside the conductor, for all symmetric cases, the conductor, all it needs to, the field is the same as if it was a thin straight wire. Okay, so that's the point of that. All right, that ends that problem.